Hey everyone, welcome back to my channel. So today we are going to learn about the linear combination span and subspace. Okay. So you may be wondering that why we are learning these concepts. Okay. So these concepts help us to understand what is a dimension, then what is a direction, and the model behavior in the data science. Okay. And these concepts are the essential foundation for data science and even computer graphics and even quantum mechanics. Okay, so now coming to this topic. Okay, there are three topics, that is linear combination, span, and subspace. Okay, so first we are coming to the linear combination. So to understand a linear combination, we need to understand why we need a linear combination. Okay, so suppose I want to reach at a any point in the 2D coordinate, suppose for this point or this point. Okay, so for this I cannot draw a direct straight line and reach to that point. Okay, so in that case I need a perfect a mathematical equation or mathematical tooling using which I can reach to the particular point. Okay, so in this case a linear combination plays important role. Okay, with the help of linear combination you will reach to this point. Okay, so we will study the linear combination further. So I have written the definition here for the linear combination. So a linear combination is a way of expressing a new vector, okay, as a sum of the scalar multiple of two vectors in 2D coordinate space. So making it more simple, I can say that linear combination is the sum of scaled vectors. Okay, so we will study how it is a sum of scaled vectors. I'm going to show you visually so you can understand more better. Okay, so let me draw a unit vector. Okay, so we have studied about the unit vector in the previous video, okay, about the vectors operation. So or the maybe in the vector introduction, the vector, the DNF machine learning. Okay, so I am drawing a unit vector here. Let me draw it once again. This is my unit vector. Okay, and I am drawing another unit vector that lies on the y-axis. So this unit vector, I can say that it is called I hat, and this unit vector is called the j hat. Okay, so what are the unit vectors? The unit vectors are the vectors whose length is equal to 1 or the magnitude is equal to 1. Okay, so now using these two unit vectors I want to reach at any particular point in the coordinate space. Okay, so and these two vectors are also called the standard basis vectors of the 2D coordinate space. So I can write this vector, okay, I hat equal to 1 0 and j hat, okay, j hat equal to 0 1. Okay, so why I'm writing it as a 1 0? Because this vector I hat lies on the x-axis. So here the x component is 1 and the y component is 0. And same goes for the j hat. Here for the j hat, the y component is 1 and the x component is 0. So now my purpose is I want to reach to a particular vector. Okay, so I am drawing one vector here. This is my vector, and this vector has a component 4 comma 2, and it is denoted by vector v. So I can write this vector. Okay, I can write this vector as a 4 comma 2 or 4 2. Okay, so using this standard basis vector I want to reach to this vector. Okay, so I am writing the equation here, that is 4 I hat plus 2 j hat. So you may be wondering that I am why I'm writing this equation. Okay, so as per the definition you have seen, okay, the new vector must be a sum of the scalar multiplication of two vectors. Okay, so in order to reach these two vectors, this vector, okay, so it should be the multiplied by scalar. Okay, okay, sum of scalar of multiple of two vectors. Okay, these are the two standard basis vector. Okay, and I'm multiplying the scalar, okay, to this, so I can write it further as which is nothing but 0 2. Okay, and my resulting vector will be 4 2. Okay, so using this equation, okay, 4i plus 2j, we have multiplied the scalar with the standard basis vector and did the sum, and the resulting vector that we want, okay, 4 comma 2. So we got this vector. Okay, so this equation, okay, 4i plus 2j, okay, this equation is called the linear combination. Linear combination. So using this linear combination, okay, linear combination of standard basis vector I and j, okay, we can reach at any point in the 2D coordinate space. Now coming to the next topic, that is span. Okay, so what is span? From the definition you can see the set of all possible vectors that you can reach with the linear combination of two vectors is called a span. Okay, using the linear combination of the standard basis vector I and j, okay, so you can reach at any point, okay, and the resulting vector, that is the set of all possible vectors, okay, so that you can reach with the linear combination of two vectors called a span. Or you can say that this means how you can reach at every vector in the 2D space using the scalar multiplication and addition. So for example, you did the linear combination, okay, of two vectors, that is I and j, and you got the set of all the possible vectors that you can see in the this image. Okay, so this is called the span of the standard basis vector I and j. Okay, now this collection of vector, okay, instead of saying the collection of vector, you can consider the tip of the vector as a point. Okay, so now going to the second image, consider this tip of the vectors as a point. So in this image you can see that these are the points, okay, that is the tip of the vectors in the infinite sheet, okay, infinite space. Okay, and when these points combines, they can form a this grid. Okay, so this is for your basic understanding. Now I can say that there is one more definition here. If two vectors lie on the same line, this is not a definition but this is a condition. If the two vectors lying on the same line, then the span of this vector will be those vectors which lie on the same line. Okay, so for example, here in this case we use the standard basis vector and we reach at any point in the 2D coordinate space. Okay, but in this case what it is trying to say, if two vectors lie on the same line, then span of this vector will be those vectors which lie on the same line. So to understand this more better, okay, I am drawing here the vector. Okay, so for example, this vector is minus 2 2 and this vector is minus 4 4. Okay, so when I perform the linear combination of these two vectors, okay, the resulting vector, okay, will be will lie, okay, will lie on this line. Suppose this is the infinite line, okay, and for on this infinite line these are the two vectors, okay, and this using the combination of this linear combination of these two vectors, the resulting vector will also lie on the same line. Okay, so the set of all possible vectors that arise from this linear combination of two vectors lie on the same line. Okay, so the span of these two vectors is also the line. Okay, because the resulting vector on the line lies on the same line, which is rather than the span of the standard basis vector I and j. So using this standard basis vector you can reach at any point, but these two vectors lie on the same line, so this its linear combination, the resulting set of all possible vectors will lie on the same line. Okay, so the span will be line for these two vectors. Now I can say that for the plane R2, okay, the plane, what is plane R2? My 2D coordinate space, okay, it is also denoted by R2 plane. Okay, so now I can say that R2 plane is the span of the standard basis vector, that is I hat and the j hat. Okay, so what is this? This is a R2 plane is a span of I hat and the j hat, means a set of all possible vectors, okay, that resulted from the linear combination of standard basis vector I and j. So you may be wondering that why I and the j, okay, why the standard basis vector, okay, can't I write any other two vectors? Yes, my friend, you can write any two vectors, but it has some condition, okay. So let me write another condition here for the R2 plane, which is also equal to the span of two linear independent vectors. Okay, two linear independent vectors. So you may be wondering that what are the linear independent vectors? Okay, so our next topic is the linear independence and linear dependence. So we are going to study about what is a linear independent and what is a linear dependent. Okay, so to understand the linear independence, we need to understand what is a linear dependent. Okay, so I am drawing here two vectors. This is my vector 4 comma 4. This is my vector 2 comma 2. Okay, so this is the vector v and this is the vector w. Okay, so I can write this vector w equal to 2v. Okay, why 2v? Because the vector w is a scaled version of vector v. I can write this as a 2 2 equal to, sorry, a scalar multiplied by the vector v, that is that result in a vector w. Okay, that is nothing but 4 4. So we can say that if any two vectors, okay, any two vectors are the scaled version of each other, okay, then these two vectors are called the linear dependent vector. These two vectors w and v are called the linear dependent vectors. Okay, now for the linear independence, if any two vectors which are not the scale version of each other, we can say that it is a linear independent vector. We got this, we have tried to understand it as a visually, but we need to prove it mathematically. Okay, so now we are going to prove it mathematically if any two vectors are linear dependent or independent. Okay, so I am writing here a two vectors, vector v, that is denoted by 1 1, and vector w. Okay, it is denoted by 0 6. Now if these two vectors satisfy this condition, that is c1 v, okay, v plus c2 into vector w equal to 0 0. If these two vectors satisfy this condition, this means if LHS equal to RHS, then we can say that these two vectors v and w are linearly independent vector. Okay, so now we are going to prove it. We can write this equation as c1 into 1 1 plus c2 into 0 6, that is equal to 0 0. Okay, so I can write this equation as c1 plus 0 c2 equal to 0 and c1 plus 6c2 equal to 0. Okay, so for this equation I am writing it as a c1 plus 0 equal to 0. Okay, so here c1 equal to 0, and for this equation we know that c1 equal to 0, so I am putting c1 as 0 here. So 0 plus 6c2 equal to 0, okay, then c2 is also 0. So in this case, okay, in this case both the vectors c1 and c2 are 0, okay. So if I put this c1 and c2 into this above condition, okay, in this condition I get the resulting vector 0 0, okay. So you can say that if the c1, the scalar c1 and c2 are 0, then these vectors, okay, are called the linear independent vectors, okay, when c1 and c2, the scalar c1 and c2 are 0. Now we will check for the linear dependent vector, okay. So I will be taking again the previous example, that is vector v equal to 2 2. The these are the two vectors that I have shown you by drawing the visually, okay. And my vector w, okay, which is equal to 4 4. So I am writing this equation as c1 into 2 2 plus c2 into 4 4 equal to 0, okay. So I'm writing again this equation as 2c1 plus 4c2 equal to 0, and the second one is 2c1 plus 4c2 equal to 0. So I can write this equation as 2c1, okay, equal to minus 4c2, which is nothing but c1 equal to minus 1 by 2 c2, and same goes for this, okay. For this equation also we get this, okay. So now for the c2, okay, for the c2 I can write it as a c2 equal to minus 2 c1, okay. So for example, if c1 equal to minus 1, then c2 equal to 2, okay. If c1 equal to minus 2, then c2 equal to 4. So we can say that these two scalars, okay, are non-zero. So in our case, this two scalar, if we put this two scalar in the above equation, then we never get the resulting vector as a zero vector, okay. So we can say that these two vectors, okay, the above two vectors, that is 2 2 and 4 4, are called the linear dependent vectors, okay. Now coming to a last topic, which is called a subspace, okay. So in the previous image that we have seen here, okay, so we have seen that this is a collection of vector in 2D coordinate space, and instead of considering this vectors, we are considering it as a points, okay. So for example, suppose this image is a coordinate space, 2D coordinate space, considering the multiple infinite vectors, okay. And now I have drawn another subspace, okay, which is a subset of this vector space, okay. So I can write this space as a vector subspace, okay, which is a subset of the parent space. Now, in order to this subspace exist, okay, it must satisfy three conditions. So you can see I have written this three condition. It must include a zero vector, it must be closed under the scalar multiplication, and it must be closed under addition. So I have written that, but we have to mathematically prove that these three conditions. So once we mathematically prove these three conditions, we can say that this subspace, okay, is a part of the vector space, and this is the valid subspace, okay. So first of all I will be considering this starting with the second condition. Okay, suppose this is my vector subspace V, which has the multiple vectors. Okay, v1, then v2, okay, v3, then v4 up to vn. So you can consider it as a this subspace. Okay, this subspace is denoted by this vector set. Okay, so now if I'm taking any two vectors here, okay, I'm taking like v3 and v5, okay, and when I multiply this v3 and v5 with any scalar value, that is c1 and c2, okay, then the resulting value, if the resulting value, okay, if the resulting value exists in this vector subset, okay, then we can say that it must be closed under the scalar multiplication. Okay, so this condition satisfy. Why satisfy? If we multiply any vector with the scalar value and the resulting vector also exists in the subset, okay, this set, okay, so this condition satisfy. Same goes for the vector addition. Okay, so if I take any two vector, for example v1 and v2, okay, if I add this two vector v1 plus v2 and the resulting vectors also exist in this space, okay, subset, then we can say that it must be closed under the addition. Okay, then this condition also satisfy. And what about the first condition? So if the second condition satisfy, okay, we can say that first condition also satisfy. How? Then we have, for the second condition, we have seen that if we multiply the any vector exist in this set with any scalar and that resulting vector also exists in this set, then we can say that it must be closed under the scalar multiplication. Now I'm taking a vector, for example v6, and I'm multiplying with the scalar 0. Okay, the resulting vector will be the 0 vector. Okay, and if this 0 vector, also exists in this subset, then we can say that this condition also satisfies. So this is the valid vector subspace. Okay, now I am going to show you visually with the Streamlit application that I have developed, so you can understand more better, okay, these topics. So this is the app I have developed in Streamlit. So on the left hand side, you can see the left pane for the vector settings, where you can vary the value of vector A, vector B, scalar A and scalar B. So vector A is nothing but vector V1 and vector B is nothing but vector V2. And on the right hand side, we can see that a 2D coordinate graph where we can visualize the linear combination of these two vectors V1 and V2. Okay, so now we can see that these two vectors V1 and V2 has a length of 1. So we can say that these vectors are standard basis vector. Okay, and this the resulting vector, okay, obtained from the linear combination, that is AV1 plus BV2. Okay, so this is the resulting vector obtained from this linear combination. So we have, what we have done is we have multiplied the scalars with vector v1 and vector v2, that is a and b, and we did their sum. So we obtained this resulting vector that is obtained from the linear combination. Now let me vary the value of this scalar. Okay, so I am little bit increasing the value of this scalar. So you can see that the direction of my resulting vector, okay, has changed, and its length has also increased. Now I am varying the value of vector v1 and v2. Okay, so let me increase the value of vector v1, that is 0, 3. Now I am increasing the value of vector v2. Okay, so it will be in opposite direction. Oh, my resulting vector gone out of this 2D coordinate graph, so I have to decrease the scalar value. So yeah, now you can see that this is another resulting vector obtained from the linear combination of two other vectors, okay, v1 and v2. So let me also change the setting. Okay, so I have changed the direction of v2, so the direction of resulting vector has also changed. I can also vary the direction of vector v1. Okay, you can see that. So what you are understanding from this, so with any linear combination, okay, with any two vectors that are linearly independent, we can reach anywhere in the 2D coordinate space by varying the value of v1 v2 a and b. Okay, now you can see here, this also tells that if the two vectors v1 and v2 are linearly independent or not. So what here it is written, the vector form a basis, okay, they span r2 and are linearly independent. So you may be wondering that what is a new term basis. Okay, so I have written here, so a basis is a set of vector, okay, that are linearly independent and span the vector space. Okay, so it is simple. Okay, basis means a set of vectors which are always linearly independent and they span the vector space. Span the vector space means they means with those vectors we can reach anywhere in the 2D coordinate space. Okay, so that is called a basis. Now we have seen about the linearly independent vector. Okay, now let me show you linearly dependent vector. So this is my vector v1 having the x component and y component as 2 2, and this is my vector v2 having the x and y component as 4 4. Okay, so you can now see here, these both vector v1 and v2 lie on the same line. So what they are scale version of each other. Okay, so you can see here it is written the vectors do not form a basis and they are linearly dependent. Okay, I hope this video helped you understand the linear combination span and the basis vector in a clear and the visual way. If you found this video helpful, then please give it a thumbs up. It really motivates me to keep making more video like this. And don't forget to subscribe and hit the bell icon so you don't miss the next video in our linear algebra series for the machine learning. Thanks for watching. I will see you in the next video.